we want to talk today about recursion. And I guess I need to be on the recursion page in order to do that. Okay. So recursion is just simply the case when a function calls itself, right? So a function that calls itself is called a recursive function. And we've already seen how the stack works in Python. And we know that we can, when we call something on the stack, we call something, a set of local variables specific to that function get put on the stack, and we can use those variables, and then when we pop them off the stack, we return to the place we were called from, and all the values from the previous program are restored. So we want to use that principle. Because of that principle, we can actually do something like this. And let's see if we can pop this into our handy-dandy Python tutor. Okay, so here is Python tutor, right? And we have the live coding exercise, and I picked up the wrong window. There we go. We have the live coding exercise, and I can paste this code into there. And as is normal when we define a function, right? Remember that this is actually running our code as we're going through. Right. So when you paste something in, when the Python interpreter encounters a function definition, what it does is it simply goes through. It makes a note that it has this function out there, blast. It puts the function into memory so it can call it. And it makes note that it has, for example, in this one, it has one parameter, n. And now we can actually call blast, and we can call it with something, let's say blast 5. And I'm in the wrong, there we go, blast 5. And we can actually see what happens here. And I'm going to take this back to the first, and we're just going to go through, we're going to walk through this one step at a time. Right? We see the function, we make a note, and now we call blast 5. So when we make our call, 5 is the argument, right? So we call blast, and we replace the parameter n with the value 5, right? So we make a note. This is the stack frame for our invocation of blast with the value of the parameter equal to 5. We walk through. N is greater than 0, so we're not done yet. We print out the value of n, right? And you can see n comes up, 5 comes up here, right? And now what we're going to do is we're going to make another call to blast. Only this time we're going to make a call with n. Instead of calling it with 5, we're going to call it with 5 minus 1 or 4. And when we do this, what we're going to do is we're going to create another entry on the stack, right? So now at this point, we have blast. We've made a new invocation of blast, right? We've come all the way back to here, right? The start of the blast routine. But where we're going to return to when this new routine ends is we're going to return right to this line in the blast n equals 5 stack, right? So we'll come down again, and we will hit if n greater than 0, and it's greater than 0. So we'll print out our 4. And now we're going to make another call to blast, again with n equals 3. And again, what we're going to do is we're going to mark where we return from so that this n equals 3 invocation, right? You notice that each one of these has their own value of the parameter n, right? And 5 there, 4 there, 3 here. And we'll walk down through again. We'll print out the 3. We'll call blast again with n equal 2. We'll print out the 2. We'll call blast again with n equals 1. We'll print out the 1. And we'll call blast again, this time with our final value, n equals 0. Okay? So now this is the concept of recursion. When you recurse, you call yourself again, hopefully with a smaller version or simpler version of the operation. So we started out wanting to blast n for n equals 5, and now we're down to blast n for n equals 0. And it turns out that this time what we have is we have a different case. N is no longer greater than 0, n is equal to 0. So we will print off our blast off. And now what's going to happen is we're going to hit our return statement for our blast with the value of n equals 0. And what's going to happen now is that, well, if we had a return value here, we would return the return value, right? And that would be returned back into the calling program. But we don't. There's no return value here. So all we're going to do is we're going to terminate this version of the blast function, and we are going to return to where we were called from in the function immediately preceding us on the stack, right? So now we come back, and we are in the n equals 1, right? We've popped the n equals 0 case off our stack. We're now in the n equals 1 case. Well, right, the only thing following the call to n equal to 0 is a return statement, so we'll hit that return statement again. This time, blast with the parameter n equals 1 will come off the stack, no return value, and we'll return to the n equals 2 case. Again, we're returning to here where that n equals 2 was called. There's nothing following that, right? The else statement is just there. So we'll return down to here. We will no return value. We pop off. We go back to the n equals 3 case in the same spot, n equals 4 case in the same spot. And now what happens, we have something different. Well, no, we have one more. Now we're in the n equals 5 case in the same spot. And now this time when we return, we're no longer going to return to a call of blast. We're going to return to our global frame, which is down here on line 9, and that'll pretty much end our program, right? And we're done. And if we wanted, we could do something like, we could put something into here. Let's print n again. Why not? And this time, let's call blast 3, just so I don't have to walk through so many times. And if we do this, and let's do one more here, we'll print done, just to show you a little bit more of, again, the stack manipulation, right? We're on the definition of our function. We've now defined our function. We've made a notation. We've pushed a frame out, or we've put it, I'm sorry, we've, in our global frame, we've put a notation for where the blast routine is. Now we'll call blast with n equals 3, right? So we've called blast from here with n equals 3. Well, I'm still going to return nothing. I was thinking maybe I could put a return value in there too, but we'll get to that with other examples. Okay, 3 is greater than 0, so we'll print out 3. And now we'll call blast with 2 again, right? We come in here, we call blast, we push our entry onto the stack frame. We print the 2, we call blast with the value 1. We push that onto our stack frame. We print the 1, we call blast with n equals 0. So that's not now on our stack frame, right? 0 is not greater than 0, so we'll come down to our else clause. We'll print blast off. And now we're ending our n equals 0 case. We're going to return from the n equals 0 case, and we're going to return to the n equals 1 case, right? And this time, when we come back, we're on the line following our call, right? Because this was a call to blast n equals 0. We'll now print out our 1, and we'll return back to our n equals 2 case, print out the 2, return to our n equals 3 case, print out the 3, and now again we've printed out. We're now back to we've exhausted all of the recursive steps, so we're now back to our global frame, and we will return back to our blast 3, after our blast 3 call, and we will print our done, and then we're done with the function. Okay, so that's recursion. And the reason we can do this recursion is because we have this call stack mechanism, stack frame mechanism, that every time you make a function call, we put everything that function call needs, including local variables and parameters, onto the stack where it's separate from any other calls to the same routine. So this allows us to so this allows us to make arbitrary function calls to the same thing. It's also why globals are so bad to use, or it's one of the reasons. If all you're using are local variables, there's no side effects, and you don't have to worry about the fact that maybe you're changing some value that another version of the routine is going to need later. So don't use globals. Don't use global variables. Use local variables. Kind of make it that way. We make the function call. When we see the call, we switch execution to the start of the called function. And then when we end, we look to the top of the stack, whatever is right after us, return any values we need to return, and then restore that function stack onto the CPU and kind of pick up where we left off before the function call. All right. I did something hopefully kind of funny or kind of funky. If you look at our results, right, the second time in particular, we counted down from 3, and then we counted back up from 1. And I want to kind of show you how that works in these next couple of examples. So let's take a look at what we actually want to do here. For this one, we're going to pass in a list. And we don't want to pass in the entire list. What we want to pass in is an alias to the list. We don't want to be breaking up our lists and creating, right, if we were to do a slicing operation, that takes a long time. We have to copy. A slicing operation actually has to make a copy of the list. So we're going to do this recursive function that takes a list, and it takes the current index I. And you guys can't see this because my auto switching isn't working. So let's go back to presenting slides. There we go. So we're going to write these two functions, rp1 and rp2, and they're going to take a list, and then they're going to take an index of the front of our list. And what we're going to do is we're going to peel off values from the front of our list one by one. We're going to work from the full list, and we're going to peel off one value at a time using recursion. And at the end, we're going to be in a position where we've peeled off all the values and we can process them. But I want to take a look at two different things. First, they both have the same first line. I just got a pop-up for Cyber Monday deals. Important in the middle of the lecture. Anyway, so they both check. They both look for the end of the list, right? If we're past the end of the list, they're just going to do a little print. And then you'll notice that this one does a print and then an RP1 call. The other one does the call to RP2 and then the print. So there's a little bit of difference, but that's really the only difference between these two functions. So let's kind of pop these in to our Python tutor. Let's see what happens. Okay, so we have this. And now what we want to do is we want to go back to the first line. Let me say, let's first call RP1. And I'm in the wrong window. So we can call RP1, and what we do with RP1 is we call it with a list, L, and where we want to start on our list, right? And then we can come through and we can actually watch this happen, right? So here we go. We see our RP1 call, we make a note of it. We see our RP2 call, we make a note of it. We create a list L. This is all in the global frame. We now make our call to RP1, and actually let me type in RP2 here as well. Okay, so now we make our first call to RP1, right? We come in, we look, we check, are we at the end of the list, right? Have we walked off the end? If we reference L sub I, are we going to be off the end of our list? No. So we'll come in, we'll print out that first element, L sub I. That is the first element, right? I is 0. First element is the value 2. And then we make an immediate call to RP1, this time with I equal to 1, right? We'll do the same thing. We'll walk down. We're still not at the end of the list. So we'll print out the value at L sub 1. We'll make another recursive call, right? Every time we make the recursive call, we're extending our stack, extending the entries on our stack. We're still not at the end of the list. We'll print out 5. We'll make a call with I equal to 3, right? We have 0, 1, 2, 3. So we have 2 more to print out. And this is just going through and it's processing our values one at a time, right? It's walking through the list from the 2 toward the 11 and processing them one at a time, right? This print can be considered to be a process. You're doing something with the information, and then it's moving on and recursing onto the rest of the list. And we can do this again, and we'll print out the 11, I hope. Yep. And now we'll recurse one more time. And at this point, I is equal to 5. There are 5 entries in our list. So this time when we come in, RP1 says, well, I is no longer less than the length of L. I is equal to the length of L. So we're just going to hit our print statement. And once we do that, this version, right, the I equals 5 version of RP1 is going to terminate and return back to the I equals 4 version. Right, so again, now we're here. There's nothing else after this. So we're in the I equals 4 version. We'll terminate that, return back to the I equals 3 version. So now we're kind of unrolling the recursion. We'll return past the I equals 3 version, I equals 2, I equals 1. At this point, we're back at the I equals 0 version. That was called from here. So our next step will return back, and now we're on the next line. Okay, so what we did was we came in, we checked our termination condition, we did something with the data, and then we recursed on whatever was left, right? We processed the ith element, and then we recursed on everything from I plus 1 down. And now let's look at the next case. If we look at the RP2 case, right, same kind of basic call, L, 0. And what we'll do here is we'll recurse through again. We'll do the same type of recursion, but this time instead of printing out anything, right, we stopped here with our RP1 call. Instead of printing out something, we'll immediately recurse to the next, right? So now we're walking I, instead of doing something, we're walking I to this end of the list, and we're not going to do any processing until we get to that end of the list. So we come down here, I is equal to 1, that's still less than 5, so we'll recurse again. I equals 2, still less than 5, we'll recurse again. I equals 3, still less than 5, we'll recurse again. I equals 4, still less than 5, we'll recurse again. And now, I'm sorry, now we're on I equals 4. Okay, now, okay, 4 is still less than 5. We will recurse to I equals 5. Right now we've walked our way all the way past the end of this list. And now what we're going to do is we're going to actually start processing. Well, 5 is not less than the length, so we'll come down to the print statement. In the else clause, we'll print out a blank line. Doesn't really do us much good. We'll do it anyway. And at this point, this L equals 5 case is done. So we will return back to our L equals 4 case. Well, L equals 4 isn't done. It still has something to do, and what it needs to do is it needs to print out L sub 4. So we will print out L sub 4, which is the 11. And now we're done with that. We're going to pop that L equals 4 case off our stack and return back to the I equals 4 case off the stack and return to the I equals 3 case. We'll print out L sub 3. We'll return to the I equals 2 case. Pop the I equals 3 case off the stack. We'll print out the I equals 2 case, right, the 5. We'll return to the I equals 1 case. We'll print out I equals 1, L sub 1. And now we're back to the 0 case. We'll print out L sub 0. And now, again, we're done with our recursion. We've unwrapped it all. We return back to where we were called from, which is line 17. Okay, so the illustration here is that this first version, operating on a list, processes the front of the list first. This is head recursion. You process the front of the head first, and then you call recursion on the tail, whatever's left. RP2, on the other hand, is tail recursion. You walk all the way to the end of the list, process the last element, and then you walk back up processing everybody else. So it allows you to do things either in order or in reverse order. Okay. Does that make some kind of sense? I'm kind of running down here and looking at the notes. Okay. Yeah, so there we go. Let me see what else we have here. All right. Let's see. I guess we're going to return to our notes now. Looks to me like we got this pretty much in hand. So those are pretty. I don't want to say sad recursive exercises, because it turns out you can make some pretty complicated things here or here, right? These don't have to be simple print statements. Print statements are substitutes for some actual work. But let's look at some actual practical implementations or reasons to use the recursion function. So first, I think I want to talk about some natural, let me see. Yeah, so when we're looking at these things, you know, we're kind of looking at them. We're introducing these things to you, and you're sitting there thinking, well, why would I ever do this? Does it make any sense? It's kind of a complicated way to think about things. And the truth is that it's complicated in some cases, but in a lot of cases, it's a very natural expression of an algorithm. And in particular, we have mathematical algorithms that are essentially recursive. So if you look at the factorial function as an example, right, n factorial is n times n minus 1 times n minus 2 all the way down until you get down to 1. And then 0 factorial is equal to 1. So you can define, right, this is kind of imprecise. You know, we could use summation notation or product notation to kind of get a better idea on this. But it's really easy to formulate this as what's essentially a recursive function, right? So n factorial is n times n minus 1 factorial. And that's a pretty standard way of writing the factorial function, right? So if you knew what n minus 1 factorial was, well, then you can calculate n factorial in one step just by multiplying it by the value of n. And of course, we still need this bottom case to kind of bottom us out and give us a place for our recursion to stop. I'm sorry, I didn't switch over again. Thank you, guys. Okay. So anyway, here's what I was just saying. Factorial function, n times n minus 1 times n minus 2 all the way down to 1. And we can write this as the product, right, from I equals n down to 1 of n times, the product of n, right? It's just the summation instead of the product instead of the summation, right? I think that's a pi. Or we can write it recursively, and here's the recursive formulation, right? N factorial is n times a simpler problem, right? If you think that the factorial of 1 is simpler than the factorial of 2, what we do is we take and phrase our complicated problem, n factorial, in terms of some simple operations that involve n, for example, and the solution to the simpler problem. So the simpler problem is the factorial of n minus 1. The operation we use is we multiply the simpler function by n, and that gets us to n factorial. And then we have to have this base case that tells us where to stop, right? Because if we don't have the base case, then we kind of march on for infinity or until we run out of stack space, which happens much faster than you think. I think I saw that question kind of fly by. This is the recursive part, right? This defines the function itself, n factorial, in terms of a smaller version of the problem or an easier version of the problem times times the current value n. So essentially, this defines some operations applied to a smaller version of the problem that get us the answer for the current level, for the current n. We also need something called a base case, and the base case is where the recursion bottoms out. It's where the answer is so simple that we can just write it. So for our blast off, right? Our blast off, we walked all the way down to 0. Our base case was the case n equals 0. And as long as we started off with a positive n, we walked down to 0, terminated our recursion, and then we could unwind our recursive stack. For RP1 and RP2, the base case is we've now walked our value I, our starting point for the list, past the end of the list. Right, so both of those are fairly simple base cases, and it's fairly easy to see that for blast n in particular, so long as n is positive, right, you're always walking n down, and you will eventually reach the case where n equals 0. There was some question about, I don't want to do this on the website, so let's just do this here. I'm going to define our blast function. There was some question about what happens if you don't have a base case or if your base case is wrong. We can do blast 5, right? And this will say 5, 4, 3, 2, 1, blast off. We can do blast 0, in which case we'll just do blast off. Or we can do something like blast minus 1. And when we do blast minus 1, I do have n greater than 0. Dang it. Why am I such a good programmer? Let's make this equal 0. Not equal to 0. We'll do a bad program instead. And everything else should still work. Blast 0 should still blast off. Blast 5 should still give us a 5. Now if we do blast minus 1, what we'll actually do is, well, we're going to keep counting forever. And kind of like we got a kill signal from submiti, what we'll end up doing is we'll getting a recursion, maximum recursion depth exceeded while calling a Python object. And it will tell us all of how it unwraps it. It won't, however, tell me the last value that it printed out. So the recursion goes pretty deep. but if you use too much recursion, you will eventually kill yourself. And when you get into the lab this week, what we're going to show you, there are a couple of places where we can actually bottom out your recursion, at least I hope so, where we'll bottom out your recursion without having to have an infinite loop, just by making recursive calls that kind of explode into something that is very big. All right, so now I have to remember to switch myself back to presenting slides window. All right, so
Hey, Professor Turner, I have a question.
sure.
Can you explain why the recursion goes backwards
Sure.
for the previous example?
So when we walk through, so this was the previous example, right? So for this one doesn't walk backwards. This one goes through just in the order we want it to, right?
Yeah.
So for this one, let's look at what we're actually doing. So we have this position value, this index value I, that's going to say what part of the list L we're going to be operating on. Where is our starting point for this list? And every time through, we're going to compare I to the length of L. We're not going to do anything with that. We're immediately going to recurse and increment I. So what we're actually doing is the first part of this program, right? None of our RP2 calls are going to do anything other than call RP2 on the next value until this completes for them, right? So if L has length 0, 1, 2, 3, 4, right? For I equals 0, 1, 2, 3, and 4, all we're going to do is we're going to make another call to RP2. The last call to RP2, the one from I equals 4, is going to have I equal to 5. And when we do that, we're going to make the call with L and I equals 5. We're now off the end of the list. We don't hit this call, so we terminate our recursion. And now what we have to do is we have to unwind the recursion. And the way we do that is for the I equals 5 case, well, we just print out a blank line and return. We return back here where I equals, we just made the call to I plus 1, and that was 5, so I is actually equal to 4 here. And now what we're processing is the value for I equal to 4. So we'll process I equals 4. That's all the way down here at the back end of the list. And once we've processed that, then we'll return to the call, right, to this call in the case where I equals 3, and now we'll process 0, 1, 2, 3, and continue on that way. So what we've actually done is we've walked our recursion variable all the way down to the end without doing any work, and then on the way back up, as we're unwinding our recursion, that's where we're doing the work. So the work gets done in reverse order. Make sense?
Why? Like, how does it go backwards? Like, there isn't any subtraction.
Right. So So let's start this again. Right, so now we're making the first call. We don't need subtraction because we make the call, I is 0, right? So we make another call from there that sets I to 1. Another call sets I to 2. Another call sets I to 3. And notice that we're making the calls right here. So when we return from this I equals 3 case, we're going to return to here on the I equals 2 case. Okay, so we don't need to do any subtraction. Right now we have I equals 4. And now we'll make one more call with I equals to 5. And now in the I equals 5 case, we're going to hit this else. And now we'll start unwinding things. So we don't need a subtraction because every time we pushed our RP2 variables onto the stack, we maintained a separate memory space. So I equals 5 here, but that's only local to this version of RP2. In the one it was called from, I still equals 4. And as soon as we exit this, we're going to restore this. So I will be back to 4 again. Right? So now we're going to hit our print. And once we do, we're going to unwrap our stack. Right? And now we're back up here, and I equals 4 again. Right? We walked all the way down. We did what we needed to do at that end. And now we're starting to walk our way back and do what we need to do here. So now we pop back. We restore all the variables, all the variable values from the previous version, the version that called the I equals 5 version. And that version, I equaled 4. And now we can begin processing. And since this was the call to L5, we've processed that. Now we can process this print, and the value of I is actually equal to 4, right? And once we do that, we'll pop back, and now we've gotten rid of that I equals 4 case. We're back into the version where I equals 3. So as we walk back through, the variables from the previous level get restored. As we terminate the call at one level, the variables from the previous level get restored. Okay?
Okay, I see. Thank you.
Sure, you're welcome. And that'll just keep going. All right, so now let's do a quick... I set up this thing to auto... I thought I set this up to auto switch to